Hello, everybody. Mike Petrillo. It's a great honor to introduce our clear speaker today, Dr. Kelly Pennell. Just a little background on Kelly. She received a bachelor's in civil engineering from Lawrence Tech in '97. And then she went and joined the real world, and she was a consultant with Arcadis for a while. Eventually, she rejoined the good folks of academia and received a master's at the Rose-Hulman Institute of Technology in 2001. And completed a Ph.D. in civil engineering, focusing on the environment at Purdue in 2005. And then from 2005 to 2008, she completed a postdoc at Brown University. Upon completing the postdoc, she received her first academic appointment, also at University of Massachusetts, Dartmouth, at 2010 to 2013. And then she was recruited to Lexington, Kentucky, as an assistant professor in civil engineering. Where she still is, and she's risen up the ranks all the way to full professor as of 2021. And along with that, rising up through the ranks, she is now the current director of the University of Kentucky Superfund Research Center. So congratulations on that. She's published extensively and has many awards. One that I'd like to point out, she has received an NSF Career Award, which is one of the most prestigious awards in that world. Just personally, I've known Kelly for a long time, so it's great to see you. I know she's been a big mentor to me, as to many scientists at Kentucky, especially for women in science and minorities in science. So thank you, Kelly.
Yeah. It's a great honor to be here, and hopefully everyone can hear me. And I'm actually a little bit grateful that we had some technical difficulties, because I noticed that I have a typo on my slide. And so now I no longer feel self-conscious about that. So here we go. I'm really grateful to be here and to be in a community of people who care about vapor intrusion as much as I do. So it's been great to talk to some of you about our common interests. So without further ado, I'll go ahead and get started. To start off, I want to tell you a little bit about the UK Superfund Research Center. It just seems wrong if I didn't tell you about them, because they're so near and dear to my heart. This is a group of us that was at the UK 2022 SRP annual meeting. That was the 35th annual anniversary for the SRP program. And we showed up proud and blue. So blue is the University of Kentucky color, if you don't know. Go ahead and go to the next slide, Mike. So at the UK Superfund Research Center, we use Kentucky as a context for a lens for us to consider many environmental health research questions. And I point to where Kentucky is because some people don't know. And more importantly, I want you to understand the context of Kentucky in that it is nestled in and includes two important regions, geographically and then in a health context. So many people understand that Kentucky is in the Appalachian region, which includes approximately, not just in Kentucky, but nationally, 26 million people. And these people are reported to have poor health outcomes in a wide variety of different, health outcomes compared to the rest of the nation. Kentucky also, the western portion falls in the Delta region. And nationally, there's 10 million people in the Delta region, and these people are also described as having poorer health outcomes as the rest of the nation. We know that within the Delta and the Appalachian region, these are inflammatory related diseases, and they're just much, much higher in those areas. And we don't really have a reason why. There's many, many reasons why. Next slide. Here I'm showing Kentucky, and again, the blue is the Delta region, the yellow is the Appalachian region. What I also show are sources of environmental pollution. These would be industrial sources. So within these areas, the Delta and the Appalachian region, and then also just other areas, but what I want you to focus on is the Delta and Appalachian regions are also known as rural areas. So nearly 2 million people in Kentucky live in those areas, and they coexist with sources of industrial pollution. We use this all as a way to contextualize our knowledge and our research and design our studies within the University of Kentucky Research Superfund Research Center. Here I show one of our current trainees, Earl Robinson, collecting water samples in one of our waterways out in Western Kentucky and the Delta region. And then I also show me and my lab with 2 trainees. We're working on a VOC sensor that does real-time sensing that's being used at vapor intrusion sites. And this is a sensor that was originally developed by a sensor company through NSF and NIEHS SBIR funding, and then through field testing, and then also validation that we're doing in our lab. It's gaining some traction and some application at vapor intrusion sites. Like many Superfund research centers, we follow the framework that we are assigned, right? We have biomedical research projects and environmental science and engineering projects. Our biomedical projects focus on disease risk prevention, and we actually focus on healthy lifestyles. So how nutritional interventions can reduce the toxicity or the toxic effects of pollutants. That's project 1. And then for project 2, we look at how physical activity can reduce harmful effects associated with toxicant exposures during pregnancy. Project 3 and 4 are environmental science and engineering projects. And in those, we look at how we can treat pollutants. So in project 3, we're looking at functionalized membranes for treating air and water. And in project 4, that's my project, we look at how we can understand how chemicals move in the environment and to reduce exposures. And we specifically are looking at vapor intrusion and aging piping infrastructure, how those can create unique pathways that cause exposures that have been overlooked. And ultimately, our goal is to improve public health. Next slide. We work with our communities in Kentucky, and that cultural context of communities that you can interact with, have long-term lasting relationships, is really something that is critically important for every Superfund research program, and ours is no different. So our Superfund research program has been funded since 1997, so we have long-lasting relationships with our communities, and we know what are the needs of our communities. We're constantly assessing them, and we strive to empower them to make the best decisions they can make with the science that we know, answering the questions that they have. We want them to make decisions about how they can protect themselves from pollutants in the air, water, and how to improve their health, including decisions they make about their diet and the physical activity. And that's really the goal of our center. I want to just tell you 2 recent outcomes that are really impactful and I think really capture things that we care about a lot in our center. And as me as a director, these are outcomes that I feel like really describe what matters to me as a director. So this first one was discussed in E-Factor, an NIEHS newsletter in April of 2023. This is an article that was published in Environmental Health Perspectives, came out of our Project 1. And it was really the first article, or one of the first findings, I believe in the scientific literature, that discussed how high fiber diets may protect against adverse effects associated with exposures to PFOS. And this is really what our research has been focused on since 1997, looking at dietary interventions that can be protective against pollutant exposures. And with things like PFOS, many times these are involuntary exposures. So knowing that diets can be protective, this is very important. And I show 3 trainees here. This is at a community that we interact with, where we work with the community to prune and maintain blackberry bushes to be part of fresh fruit consumption at senior centers. Blackberries are the state fruit of Kentucky. And this is an ongoing sustainable community project that has been maintained and ongoing at many senior centers across the state. The next environmental factor story is one that we are incredibly proud of because our trainees are just the heart of our Superfund Research Center. And this is Raleigh Mills. So Raleigh Mills was just announced as the recipient of the 2023 Wetterhand Award. He received this in December. And Raleigh is just an exemplar of what we look for in our trainees. So Raleigh has worked on water filtration and membranes to treat air and water designed all different kinds of membranes and functionalized membranes to treat different types of water pollutants. And during the COVID-19 pandemic, they actually pivoted and developed air filtration devices to treat SARS-CoV-2. They have numerous patents on this. And most importantly, Raleigh on his own developed a community project where he goes and speaks with K through 12 students in Appalachia. His organization is called Innovate Appalachia, and Raleigh does this on his free time working with communities. And for our SRC, that a trainee would take this much initiative, cares this much about Kentucky, Kentuckians, cares about the science, is innovative, eager to pivot, even when something like a global pandemic hits. This is absolutely what we just love about UKSRC. So with that, I'll get into my own research. I will switch gears and talk about sewer vapor intrusion. And this will be a bit of a journey of my own here. So I began working on vapor intrusion back when I was in Rhode Island, when I moved to Brown after my PhD, because the Rhode Island Department of Environmental Management came to us and requested we work on it. We started doing what any great engineer would do. We modeled it, and we became very proud of our models. We did computational fluid dynamics models. We developed more models. We thought these models work so great. We published one of our first models in 2009, and we started doing more and more modeling. And I thought, gosh, I've really challenged this model a lot. I think we're ready to go into the field. And so we did. Next slide. And as an inspiring person that I am, I convinced other Superfund research programs to go with me. Thank goodness. And so we went into a community, the Metro Boston area, and we had 3 Superfund research centers going. We had people from College of Public Health at Boston, and I had a longtime colleague and mentor of mine, Eric Suberg at Brown University. And we went in and we were going to start drilling holes through, and we did basements, backyards, collecting indoor air. Next slide. And we did all of that. We took geoprobes into people's driveways. You can see that these houses are very close to each other. A driveway is all that separates them. We recruited homeowners to allow access for sampling, so they had to opt in. This was Madeline Scammell from Boston University School of Public Health was part of the recruitment of these property owners, homeowners. We partnered with state regulatory agencies. We interacted with responsible parties. This is very exciting. And I will tell you, as an engineer, I thought certain we were going to validate this really great 3D computational fluid dynamics model. But notice in the right-hand corner here, I had learning and integrating. There was a lot of learning to be done. Next slide. When we were doing this, it was based on a classic, and now I know outdated, vapor intrusion conceptual model. It was included in the EPA draft guidance of 2002. We were out there in 2009, 2010, 2011. It was a multi-year study. And I will say most people were really accepting this conceptual model. It was very much out there, not just us, nationally it was accepted. So the idea was that vapors migrate up from contaminated groundwater and it moves through foundation cracks. That's how it's getting in. This is a conceptual model for most radon intrusion as well. Next slide. So this is us with 2 research assistants, Jen Ames, who's now works, I believe, for a consulting company in New York City. And I'm right now forgetting her name, as I was just going to say, oh, Jen Ames, I'm sorry, she went to Berkeley. And Lee Figuelli, who is works for a consulting company in New York. But you can see we were very much invasive in people's spaces, but they had welcomed us in. And we did a lot of testing. You can see at one point we nearly hit an unmarked utility, but we had been hand augering through, so we did not hit anything. Next slide. And we made a discovery. We learned that during our indoor sampling, we were getting higher concentrations on a second floor indoor air than we were in the basement. This made no sense. And at first, I was like, let's just collect another sample. This makes no sense. And it absolutely is messing up my validation of my computational fluid dynamics model. And my lovely colleagues who are in public health said, Kelly, but this is a public health risk. And I said, it may be, and let's collect another sample. And we continued to talk about it. The reason being is that that basement had already been mitigated. So in vapor intrusion, the way you mitigate is that you depressurize the basement, you usually have a vacuum extraction well, and the entire basement had been sealed. So they had epoxy in all the walls. So my engineering mind said, this is not a vapor intrusion problem. Let's sample again. And again, my great public health colleagues who are now near and dear friends of mine said, Kelly, but it is a public health risk. I said, but my model. I said, Kelly. So we did this. And it really wasn't that much of a back and forth, but it really, all of us were kind of like, this is very odd data. And why is there this sewer gas smell? And why do we have slightly higher concentrations where there is sewer gas smell? In hindsight, this makes a lot of sense, but when you're in someone's home and you're trying to make data and you're getting data and it's taking 2 weeks to get your data, it's very hard to put all together. Next slide. It turned out after a lot of back and forth, a lot of thinking, and I don't like the term overthinking because I think I usually think just the perfect amount, we discovered this was coming from a faulty toilet connection. So all toilets have a wax seal on them. If you've ever sat on a toilet that's slightly jiggled, it might be the wax seal. If you've ever smelled sewer gas, it means sewer gas is getting into your building. What we discovered is that this sewer gas actually was a main source of PCE in the building, and that the mitigation system that was installed and approved by the regulatory agency was actually not mitigating the vapor intrusion risk. And so the vapors were coming through a faulty toilet connection. When we repaired the toilet connection, sealed it, there was no more PCE in the building. This had been completely overlooked because the standard procedure for sampling is only sample on the lowest floor. The same rationale that my engineering mind was saying, why would it be higher up above? We should sample on the lowest floor. Vapors come in from the basement. It was that conceptual model. Next slide. Our findings were published. It created a lot of people doubting us and then people coming forward and then back and forth. It was a bit of a real disruption. Then it made it into the finalized EPA vapor intrusion guidance. So you can see, as I underlined here, they actually say vapors can also enter structures that are not intended for human occupancy through sewers, drains, whatever. And so suddenly this went into the guidance in multiple places. If you now search the 2015 finalized vapor intrusion guidance, it has sewers multiple places and it lists our finding from that study that was originally only supposed to be validating my model. And our significant accidental finding was that sewers are a significant entryway for vapor intrusion. And so thank goodness we questioned ourselves. The issue with why I said it caused a disruption is that suddenly, who's responsible for that? Is it the city? Is it a municipality? Is it the responsible party? Is it a homeowner? Because remember, it was a faulty toilet seal. Who's responsible for that? Should the city, were they allowing discharges? Oh, but their sewers were really, dilapidated. Should they have been maintaining that? Suddenly, it's just a blame game. And that was very difficult. Next slide. Sewers, if you don't know, are a major infrastructure challenge. They leak. They leak a lot. And so if you are not expecting them to allow contaminated water to get into them, you have a faulty conceptual model. There are over 1 million miles of sewers in our country, and we largely do not think about them. And many of our sewers are broken or leaking. Next slide. This is just a hypothetical. I'm not saying this is true at this site, but what I want you to consider, here is a 5-mile TCE plume. It happens to be in Michigan. When we think about TCE plumes, we are very quick to think about groundwater contamination and putting people on drinking water, alternative drinking water. Over that 5 miles, we need to think about what is atop that 5 miles. So a 5-mile groundwater plume is below ground. But on top of that are entire cities. infrastructure, so much else. You've entire communities. Have we thought about all of that? We think about the public wells. Those are quick for us to reduce risks to. What are the other potential exposure risks we should be considering? And have we considered them? Alternative pathways that promote vapor entry into indoor spaces have not been adequately conceptualized or mitigated, typically. Next slide. Here's a study we did in Mountain View, California. We continue to work in that area quite regularly. Here, what I'm showing you here in pink is what was the vapor intrusion study area as defined. That pink area was associated with a TCE plume that's associated with a Superfund site. The blue area is considered an expanded vapor intrusion site that is due to sewer system, VI. If you look at the scale, you can see it's a quite large area that was expanded. All of those include buildings, they include homes, they include dwellings. When you only consider that conceptual model that was the classic, you completely miss that. If you look at the yellow circles, you can see that there were hotspots there from when wastes were previously dumped down there. There was slumping in the sewer line, there were cracks there, and there are hotspots in the environment there. We did a lot of work on that to conceptualize it. We've published it. And then the bottom are pictures of my group and collaborators doing field studies there. Next slide. While we were there, we collected many samples of about 40 different manholes and cleanouts in the sewer system. We did what's called TO15, where you collect air samples and vapor samples in SUMA canisters. We did passive sampling. We collected some sewer water sample. And then we also looked at videos of the sewer. Next slide. What I want you to think about is a manhole and a cleanout and how I'm using those terms. So I show them both here. A manhole is typically in the street or in the right of way. A cleanout is typically near a home or right up against a home. What connects those two, the sewer main and that cleanout, is called a lateral, typically. If we are detecting vapors in a cleanout, a TCE vapors in a cleanout, that really means that they're very close to getting into a home. So the questions are, how do we keep those TCE vapors from entering a home? Typically, you might think, well, we have plumbing traps, right? We all have seen things underneath our sink. They don't get into my home. There's very little stopping those vapors and sewer gas from getting into your home. And then I want to just say, why do we have so much variability in sewer gas concentrations? And I'll show you in a minute, we do have a lot of variability in sewer gas concentrations. I'm not showing you a lot of data today. If you want to see it, I can send you publications. Next slide. Here is some data from all of those manholes and cleanouts that we collected. Even though they are very close to each other, this is what I'm showing you. There's a lot of variability spatially. We also see a lot of variability temporally. We've investigated reasons for that. I'm happy to discuss it with you offline. But you can even see that the cleanouts, we compare them to non-residential screening levels and residential screening levels. Many of those cleanouts exceed those. Now, people aren't breathing sewer gas from a cleanout. The idea is we don't know what an appropriate level is. We don't know how much dilution you would get before it comes into indoor air. We can do modeling to figure that out, but still there is a lot of question about that. Do we need to mitigate that? Don't we need to mitigate it? And we were one of the first ones to start publishing this. I would say we were probably the first ones to publish this. Next. And this is the publication. This has had a lot of direct influence on regulatory guidance, field practices, and nationally and internationally. Denmark is doing a lot of sewer gas vapor intrusion work as well. Next. We have done some modeling to better understand what transport mechanisms impact sewer gas transport. I said, like, well, why is there so much variability from one manhole to another? We can kind of start to get an idea about that. Why is there so much variability temporally? We can kind of start to get an idea about that. We've developed this model and we've compared it to some field data, and we have decent agreement between it. Next slide. We also included different sewer features to account for. So if you have a lateral coming in and someone is discharging clean water, that actually changes your sewer concentration in there. And so we've tried to account for many different features here. And again, we're seeing some agreement. Next slide. We published this in 2021. Still, this recurring thought is, if you know that your source of the contaminant is in the sewer main, what can you do to prevent it from getting into homes? And this has been a really big sticking point for how you mitigate this problem, right? The typical vapor intrusion mitigation is that you go and you put it in beneath someone's basement. This is not a basement problem. So how are we going to mitigate this? A big pushback has been everyone has plumbing traps. Has anyone ever seen one of these underneath your home, in your kitchen sink? Now I will say, has anyone ever had a bucket or something beneath your kitchen sink because one of these is dripping? Yes. The other thing is, you notice they are typically hand tight. Many of these are called DIY. You do them hand tight. Let's imagine that you drop something down it, you clean it out. You're hurting your back to get down under there. You're not making sure it's super tight. You're making sure it's not leaking water, and half the time they're not lining up right. So then that's when you put a little bucket under there. If it's even dripping water, you're absolutely getting vapors into a home. These are typical. If you Google this, you see 1,000 of these. Next slide. We are now doing tests in our lab, looking at plumbing code joints and seeing how much leakage we get out of them. We have tested several of them. Our hypothesis was, if they were installed properly, they likely wouldn't leak. Our hypothesis was wrong. When plumbing fixtures are installed due to code, they do not leak water. Many of them do leak vapors. And so one that is problematic, which many regulators in field and vapor intrusion professionals have noted, is a plug, the floor plug that many people have in their basement. Even when that is installed properly, it still leaks vapors. And that is where we see a lot of sewer gas intrusion occurring. And so now we actually have quantitative data with that using a pressure logger, and we're continuing to do some tests. So now we're getting quantitative data that we can publish so that we're no longer told, oh, it's a homeowner's fault because they don't have their fixtures installed right. Even when they are installed right, they're still prone to leaking gas because these aren't installed to not leak gas. They're installed to not leak liquids. Next. A site we're working on is a multifamily development. That same question of how do you stop the vapors from getting into that whole community if you know the sewer main serving that community has TCE in it? We've actually investigated using sewer siphons, which are not typically advantageous. A lot of cities will say don't use them, but the alternatives are things like installing an entire vent on a sewer main and venting out all that sewer gas. You have to treat that with carbon. You have to do operation and maintenance on it. You can install special traps in every single home. Those have to be maintained. You have to get access agreements. We've installed in this community, I will say the regulator has installed in this community multiple traps now, these siphons, and they're seeing good progress with them. They're seeing reduction in TCE so that by the time that they're at the other side of the lateral, the TCE has decreased. So we removed the source from getting into the community. And so we are working on a publication with that. The last thing I'll end with is just a summary of how weather and building construction can impact the potential for vapor intrusion. Another thing with conceptual models. This conceptual model, or one like it, has floated around for a very long time for vapor intrusion. Conceptual models show these effects, that there's wind, there's these streamlines, there's a vadose zone, there's all these complicated factors. The reality is that very, very few vapor intrusion models, even the ones that are recommended by EPA for screening, ever really included above ground processes. They included only the subsurface. So our group said we are committed to interweaving both the subsurface and the above ground spaces. So how does wind and weather and the actual indoor air, can we actually model all of that on the indoor air to get a better estimate of vapor intrusion risks? And so we did things like looking at how building depressurization is impacted by wind speed, direction, temperature differentials, seasonal effects. Because if you look in the literature, people have all kinds of claims about seasonal effects and very little theoretical backing for this. And so we wanted to look at it from a mechanistic standpoint, and so we did that. Next slide. We used a house that the Department of Defense had funded a multi-year study at called, and it was like lovingly referred to as Sun Devil Manor. Paul Johnson, who's now the president of Colorado School of Mines, at the time he was the dean at Arizona State University, purchased this house with the intent to outfit it as a vapor intrusion lab. So it was completely outfitted, and it was on the edge of a plume associated with Hill Air Force Base. And so in the bottom there, I circle about where the house is. So our group went there, and many researchers could use this house to conduct experiments there. And so we went there and took all kinds of measurements, used some weather data from it, and used the mass flux measurements that they had been collecting over many years. Next slide. This is a picture of the basement, just so you see that when I say they did outfit it as a lab, you see it is. They had many GCs in there. They would collect data 24 hours a day, 7 days a week. They had years and years of data on this site. They also looked at air exchange rates, and they collected TCE indoor air concentrations at this site. Next slide. What we did was we looked at a modeling approach where we could couple, again, how weather was impacting this, what they were getting from mass flux into the home from the subsurface, and then also model indoor air. And no one had done that. In the past, all that people did was just look at a vapor intrusion model, which was only looking at the subsurface. Next. We decided not to use a vapor intrusion model and instead, next, use the field measurements that they had been collecting for many, many years. They had actual data of what the mass flux of TCE was into this house. We used that and then modeled indoor air concentrations and looked at wind effects and pressure around that home. Next slide. And we use freely available software that's maintained by NIST. What we learned is that the orientation of the building to wind is very important on the air exchange rate. It also is very important on determining indoor air concentrations. And so when you look at a community like this, where say a overhead garage door might be situated in a different direction than the neighboring or say the one behind it, you get a different indoor air concentration. So it's very important to understand how the air physics are going to impact the indoor air concentrations. One thing that has been written up in the scientific literature about vapor intrusion for a long time is that the data doesn't make sense. This home had different results than this home. And this home over here had different. And so communities look like, oh, things don't make any sense. But people haven't asked really difficult questions. Well, what was the indoor air like? What were the buildings situated like? What was the leakage like from that building? And we finally developed a model we could start asking those questions, which is a science that building science and indoor air communities had been using for a long time. We were able to bring that into the vapor intrusion community. Next, we published this and we showed that we had good verification between what they had been measuring for many years at this study site and with our modeling. The other really important thing that I want to point out here, this house that they invested, it was multi-million-dollar study that DoD invested in. They had multiple years of data on. And this too was a house that they found a land drain at that was a source of TCE. They assumed the conceptual model was right, that it was coming only from a groundwater plume, that classic conceptual model. And it wasn't until many years into the study that they realized their conceptual model was wrong. And a large portion of this was actually coming from a land drain that connected from a storm sewer to the home. So getting that conceptual model right, questioning your conceptual model, asking, is this data just wrong or is it making sense? How can I make better sense of this? This was really a critical learning point and turning point, and it validated what we saw way earlier in Boston. And now I think the community is really like, wow, these conduits are really important, but we don't always know they're at sites. And so this is really important. So the lessons learned are to always ask, what are you thinking? And that's been a major, major thing in our group for vapor intrusion. You're starting down one path, assuming, for instance, this classic conceptual model is right. And when you get data that doesn't make sense, you're not throwing it out, but you keep trying to make sense of it with this understanding. And the best discoveries we've made, and I feel like the most impact we've had, is when we stop and peel across the layers and just say, what are we thinking? Next slide. There's this conceptual model that really was around for 15 years, more than that. And now we have learned that actually it matters what's going on in the house, ventilation in the house, that vapors come in through cracks. It also comes in sewers. It matters if the joints in piping systems are leaking or not. It matters if how the sewers are partitioning vapors. It matters what the sources are in the vapors. We have to keep thinking about the sources and what source is most relevant for that site. Taking these generic site models and not thinking them through causes all kinds of confusion when in fact it's just a complex process that we can figure out. Next. So I love this quote just about using small scale models and being aware of the mental models that we apply to the external world. This is something that we do a lot in my research group, of always questioning our conceptual models, refining and redefining our conceptual models, always thinking it through. So I'll just read the bottom part. Engineers and scientists establish conceptual models on their mental models to develop solutions and interpret data associated with complex environmental systems. We benefit from really understanding problems before jumping into defining our models and then our solutions. And that's, I think, our biggest lesson learned, was really question those mental models before we jump in to solving something or thinking that we understand something. So I just want to acknowledge everyone that's worked with me, my current research group, which I have pictured here, and of course the funding that makes everything happen. And next slide, and that's it. And I'm happy to take questions.
So the aspect of coming from pipes or the ground, at least, is that basically intruding them from the outside, or is that people creating the waste and putting it in, or both?
Well, we know for certain sites, and it's a really good question, and there's multiple sources that where VOCs come from in sewers. So VOCs in sewers come from what are called industrial treatment permits. So it depends if your pre-treatment permit, meaning that an industry has a permit, it depends what they're allowed to discharge. So at the site that I referenced in Boston, we just looked up what their typical discharge limits were. And they were given for like total VOCs, and their total VOC limits were like 500 ppm, which is like way more. If you look at the partitioning, say, like hypothetically, if that was all TCE, oh my gosh, that's huge. So it goes into that these aren't all integrated as far as what would be health protective, right? And I may have misquoted that, I want to say, my point is that if you have like a total VOC, right? Now, if it's an industrial pretreatment permit, they've probably done it based on what the wastewater treatment plant can handle when it gets there. They are not looking at it based on volatilization in the sewer. That's one source. Another one is, as in my example of like you have a 5-mile plume, if that sewer intersects groundwater, it's very important to think about the sewer depth and the groundwater depth. If they are breached, like you have a leak in it, groundwater, contaminated groundwater can intersect that sewer, feed into the sewer. As soon as that happens, it's going to volatilize in the sewer. So then you have contaminated groundwater being a source of VOCs in the sewer. That's another one. So there's many different sources, and we typically develop a conceptual model for that to figure out what is a primary source. Another one that has been problematic in some states is if you have a remediation system that's pump and treat, and you're treating, but and you get to discharge to the wastewater treatment plant. And so your discharge limits are high enough because you know you're going to a POTW, that is a source. But in the meantime, you're discharging to a sewer, which then can volatilize. So there's many sources. It's important that you think about all of those inputs that can volatilize.
And then, so one thing that we found in the drinking water is that we or get put into the ground.
Mhm.
Some of them actually are really good at VOCs transporting, especially like gas station.
There's a
Do you see-
request,
do you see
repeat
that?
the question.
Oh, so the previous question was just how are VOCs getting into sewer systems? And is it one source or multiple? And now this other question has to do with. Right. So the other question is, does pipe material make a difference? And I will say, yes, pipe material makes a difference. So we had, I had a student looking at basically risk levels for breakage of piping, because you can look at piping material and the risk of breaching, right? So some pipes are newer and a lot of, municipalities are changing out some piping. So you have PVC or vitrified clay pipe, or you have, and clay pipe, those joints are almost always offset. In addition, they will also sometimes crack. Sometimes sewer pipes, you'd be surprised, are almost just now like an open, like gravel hole practically. Yes, the sewer pipe does matter as far as the integrity of the pipe being left. And there is data actually on that.
So I guess hypothetical situation, say you're a homeowner in Florida with no anthropogenic VOCs of the exposure varies across the city. Let's just say you're in an area of whatever you want to catalog as average exposure for total VOCs or any given VOC. This is kind of a two-part question. One, what is the amount of variation amongst the city block of homes? And two, is it possible to create a home that's VOC free? And is that financially feasible for a middle class person?
Right. So the question is, what is a typical variability across a home in an area that's known to be with a high level of VOCs ambient, is what you're saying? And then also, is it possible to make a home VOC free? And I would say, one, I don't know exactly the variability across that. There have been some studies, like there is this compilation study of indoor air background studies in the US, and it does vary quite a bit. The other thing that I will say is it has a lot to do on, like, just because you might be in an area that is, might be considered like, a lower economic area or something, it doesn't necessarily mean you would have different air quality. It could mean that you're paying higher energy rates, but you might have more leakage in your home. And so you have different air exchange rates. So I just want to say that. The other thing that I would say is that VOCs are in commercial products a lot. And so it's very hard. Like, one thing that we published a paper on, what I published with an anthropologist, was on source science and vapor intrusion. So vapor intrusion spends a lot of time determining where did the source of this come from. This, I think, is getting to your question. Was the source from the contamination caused to groundwater by this industry, or is a source from the fact that the homeowner is bringing VOCs into their. The thing is that many homeowners have no way to distinguish, or sometimes even an awareness, that they're bringing VOCs into their home. And so there's a lot of time spent on making sure that because vapor intrusion is a highly regulated field, it falls under hazardous waste. And so an industry, if a responsible party is there, they're not going to pay for something that is not theirs, right? And so I would say that you can have homes that have much lower VOCs, but it is very difficult to have a zero VOC indoor air space because they are prevalent in our our consumer products.
An extension of that, if you were to get rid of all VOC products, do you think you could have a VOC free space? I think there's all some leakage from something in here.
I don't think I can answer always and never questions. So the question was, do you think you could have 100% free VOC space? And my question is, I think that you can always have less. I don't know that you can, I think it's very hard to approach zero. And my reason for that is even most people have some use of petroleum products, even myself. And I think you can use those safer and you can use those more responsibly. But, you know, if you have an attached garage and you have a lawnmower and you have a gasoline can, you've exposed yourself to benzene, toluene, ethylene, xylenes. I mean, that's just going to happen. And so you can store that safer. You can be aware of it. You can choose to put it in different places. I think there is a low awareness in the general public that is getting into your indoor air. And I also think you can do things like when you smell sewer gas, go ahead and check your sewer gas is not good for a number of reasons. It's not just because we found out that vapor intrusion contaminants can get into it. You can check your plumbing traps. Like plumbing traps, the reason that we have plumbing traps is because we did not want sewer gas in our homes for a whole variety of reasons. You can look back at public health. So I think there's a lot of things that just in general we don't do that are health protective anyhow. Mm-hmm.
I just wanted to know what would the cost be of one, or is it given by the government, or what is, how feasible that is?
So the question is, how much does it cost to replace a plumbing trap if it's faulty? Or do you mean if you're at a vapor intrusion site?
So that you have vapor intrusion house or coming from as mentioned, and some one of the mitigation strategy mentioned was gas trap or siphoning. How much that would cost, and would that be on the homeowner or?
Right. So the mitigation scenario that I didn't show a lot of detail on, but it was a siphon that was put actually in the lateral, and that was actually done by as a mitigation technique outside of the home completely. So the homeowner was not responsible for that. And that's what I would recommend, so that homeowners are not responsible for it. If you did want to maintain your traps, I mean, that is something just like home maintenance, like changing out your light bulbs that you could be doing. And of course, affordability depends person to person and household to household. But typically, those are not super expensive. I do think what our lab right now is testing is which ones are more prone to leaking, and then can we design those to be, you know, gas tight. The reality is they weren't designed to be gas tight because they weren't concerned about that. Whoever that was when they were designed. And then we're looking at alternative designs to make them more health protective. Right. So one of the questions is which time of year tends to have the highest indoor air sewer gas concentrations? So there isn't just one time of year is an interesting thing. It does depend on temperature differentials and wind speeds. And so those don't always coincide. So it does just depend on looking at the pressure differentials and the temperature differentials. And so rather than looking at seasonality, which has often been reported, we tend to tell people to look at temperature differentials. And then also look at if there's a sudden wind speed difference, because what we do see is that gusts do actually change those instantaneous concentrations. And so to look at that, a lot of these vapor intrusion measurements are tested like one day and then you don't go back for another time. And so in those short times, it looks like a big difference, but in fact, what you may have captured was like a low pressure event or something. And that's what I was saying. Yeah. So like if look at the wind and see if you're having like high wind events, be aware that I wish I don't have it right in front of me, but to look at really where the leaky side of a building is. So for instance, if you have wind, and you can typically figure out where the direction of wind is, if you have wind that's going to be on the leaky side of your building, that's going to change typically. You'll have more dilution inside as opposed to a building next door. Look at where that leaky side is. And you can make those generalizations, and those haven't been done in vapor intrusion assessments. And that's really something nice. Great. Thank you, Rich, for posting that. So so if you don't know, Rich is the vapor intrusion lead at EPA headquarters. Rich, I'm glad you're online. And he has just posted this GWMR article about new nomenclature for vapor intrusion. Thank you, Rich. And I hope I didn't say anything that didn't align with that.
When you're doing field work for the sewer sample, how far are you chasing the plumes? Is that I would imagine it could go on for a wide area.
Right. So the question is, when we do sewer sampling, how far do we chase the plumes? And actually, we don't chase the plumes. It has a lot more to do with what's coming into the sewer. So it does matter. Like, for instance, if you're getting contaminated water that goes through a crack, and then it's just figuring out how long that volatilization is going to stay in the sewer, and also what other sources enter into the sewer. You know what I mean? And we've just been really surprised by suddenly we're in a sewer and we're kind of waiting for that to go. Then we get another source, and it turns out we've suddenly found another source. And oftentimes it had to do with that sewer was leaking, or the sewer invert and where the groundwater table intersects, because you have groundwater fluctuations. And the unfortunate thing, it seems that sewers are always like just a couple of inches from the groundwater table. So that groundwater table is always like fluctuating. And it really does matter, like if it's in it, or you know what I mean? That has been a major factor. And, it is just like a couple of inches fluctuation, and it changes your data. So really having a good sense. And unfortunately, there's not like piezometers or groundwater wells right next to the sewer. So getting an idea of, are we in the water? Are we not in the water? Is really difficult. And that's what is typically whether or not, do you see what I'm saying? And at a lot of the sites, you don't have like 3 feet between the sewer and the groundwater table. It seems like our bad luck is always like, oh, we're right near the groundwater table. And that's been a real challenge. Yeah.
Something, did you do something like a different weather, like dry weather, where it's like rain? If you did see some different weather?
We have done sampling in a lot of rain, unfortunately. I have not done, I don't have the comparison data for dry weather. There are a lot of vapor intrusion, like scientists and professionals that have tried to compare some of that. I'm not one of those people, but no, I don't have the comparison data. Well, it will. You'll get some dilution. More important, I would say, is that what we have seen is when we get a big water event, and this happened at our Boston site, we actually had a clay lens or a less permeable lens. And that water actually pooled on that and left a little plateau. And then the vapors did not go up. And so we had this, it actually was protective of vapors getting up. And then so during the freeze thaw, once that went away, the vapor intrusion potential went up again. And that did really complicate data, right? So there are some times that happens, but that's more of a soil moisture issue or a soil set. And it's just that lens. Like, we just had this very weird layer where it was very tight and the water would pool there and then it would go away. Okay. Thank you.